Well, good afternoon, everyone. Hello there. Welcome to the Academy's Morrison Planetarium and to this presentation of our final show of the day, a tour of the universe. Now, this is one of several different shows that we have here, and we certainly invite you to come back some other time and join us for our others, unless you've seen them already. How many of you have seen our other shows today? Dark Universe or Expedition Reef? Okay, a few of you. Welcome back. Well, this is a different kind of show from those others that you saw. This show is entirely live, and what it is a piloted, guided tour of a three-dimensional model of our universe. So you're going to hear my voice throughout as I take us through this 3D model of the universe. And in fact, the software that we're using is something that you can actually download for free. It's a NASA-supported piece of software called OpenSpace. And if you're interested in what you see on the dome here during the next 30 minutes, you can come and see me up at the control booth after the show, and I'll tell you how you can get this piece of software. And since it is basically a free flight through the universe, I'll try not to fly too wildly and fly into any planets or plunge into any black holes, but because of the nature of the planetarium experience, because you're looking at an image that goes out to your peripheral vision, if at any point the immersiveness makes you feel a little uncomfortable, just close your eyes for a minute or so, and any sensation of discomfort should go away. So we're going to travel from Earth way out, away from our solar system, out of the Milky Way galaxy, and out to the edge of the observable universe, and then be back in time for museum closing at 5 o'clock. As with all of our presentations during this show, we'd appreciate it very much if you could please refrain from eating, drinking, snacking, or any kind of photography or recording. This would also be a great time to silence your personal electronics and to tuck away any light-emitting devices such as cell phones, tablets, flashlights, cameras, etc. That light can be very distracting to the people sitting around you in the dark and can also interfere with the images that we project onto the dome overhead. At the end of the show, we ask everyone to please exit out through the doors at the top of either stairway. Now, it doesn't look like it, but if anybody might have problems getting all the way up these stairs, just stay in your seat, and our staff will assist you later out the lower exits, if that's more convenient. But everybody else, please use these doors at the top. And at the end of the show, it will be closing time for the museum. So please proceed directly toward the exits from the Academy. So with that, we invite you now to settle back in your seats and make yourselves comfortable as we take off on our trip into outer space. And to do that, I'm going to have to change the lights in the dome and make it look like we're somewhere else, which is what planetariums do best. But to travel into outer space, one thing we can consider is that, according to one famous astronomer who said a number of years ago, outer space is not that far away. It's only an hour's drive if cars could go straight up. And we're going to start about 1 kilometer up above the surface of the Earth. And we'll see how far away outer space is. Now, if you can't guess where we are 1 kilometer above pad 39A at Cape Canaveral in Florida. So right below us is the launch pad that is used very often by SpaceX to launch payloads and crews to the International Space Station. Not too far away is pad 39A, which is over there to the left. That's where NASA plans to launch its big space launch system as part of Project Artemis in the next couple of years. But now let's move higher than 1 kilometer up, so we can get a better overview of the scenery around us. Here at Cape Canaveral, there are a number of very, very interesting things to notice. Down in the lower left there, that's the runway that was used by the space shuttle up until 2011. That's 3 miles long. And not too far away from it is the vehicle assembly building, where really big rockets like the Space Launch System are built. Down along the coast, down to the right, are all sorts of other launch pads and landing zones for the rockets that lift off from here. And we're going to go up to the edge of outer space, which, as I said, according to one astronomer, is only an hour's drive away. What does that mean? Well, if cars were going at about 65 miles an hour, in 1 hour you'd go about 66 miles. And so the edge of outer space, according to many astronomers' calculations and according to international agreements, is 100 kilometers above the ground, or about 62 miles. So that would be like the distance from San Francisco to San Jose or up to Santa Rosa. And the reason this distance is used is because up here, 100 kilometers above the ground, the air is so thin that air-controlled surfaces like wings, flaps, rudders don't work. To maneuver around, here where the air is so rarefied, you have to use rockets to maneuver around. So that's why this altitude is used as the definition of outer space. But it's not constant. The atmosphere does expand and contract, so it does change a little bit. It varies. It's not a constant 100 kilometers. There's not a sign somewhere that says outer space begins here. Because of solar activity, the atmosphere can expand. It can be a little more than that. Sometimes it can be a little bit less. But now we go from the edge of space up a little bit higher, about 4 times that distance, to 400 kilometers, right about here, which is about 250 miles or so. This is the altitude at which the International Space Station orbits the Earth. So this is the kind of view that the astronauts have from up there, 400 kilometers up, circling around the Earth once every 90 minutes, or traveling at a speed of about 17,000 miles an hour. So this is the view that we have from way up here. This is as far as people travel from Earth at present. Of course, about 50 years ago, people traveled even farther than that. So let's travel up farther away from our planet, higher than any astronaut has gone, and we'll go out about 1,000 times farther than the altitude of the International Space Station, out to where the moon is, about 250,000 miles away. And to navigate to the moon, I have to back away even farther than that so I can see the moon clearly. And let me put up its orbit so I can actually see it a little bit better. Let's see. There's the orbit of the moon right there. So the moon is to the, let me change our angle just a little bit. The moon is right behind Earth there, which isn't too bad. I didn't get too far off, out of line. So we will travel to the moon now. It took the Apollo astronauts 50 years ago about 3 days to get to the moon. And we'll do that in a lot less time. We don't have 3 days. So we'll get there in just a few seconds. And when we do, we'll see the moon. Our nearest neighbor in outer space is a dry, barren rock up there. It has no bodies of water, no atmosphere, no life on its surface at all. But when early astronomers looked at the surface of the moon, they saw those dark, flat areas, those grayish areas, and thought they were bodies of water. They didn't have telescopes to see as well as we can see the moon right now. But without telescopes, they thought those dark patches were bodies of water, so they called them seas and oceans. Well, they're not bodies of water. They're large, flat plains of dried, cooled lava. They're rock. And they're dark because they've got a higher concentration of iron than the other parts of the moon. The other areas, the lighter colored areas where we find a lot of craters, are known as the lunar highlands. And of course, the craters on the surface of the moon are huge pits that were blasted out by the impact of asteroids and comets in the past several billion years. This crater that's centered in our field of view right now is called Copernicus. It's about 60 miles across, just to give you an idea. So it's as wide as the altitude defining outer space, just about. So some of these craters are really, really big, and others are really, really small, as you can see. There are lots of different sizes up there. But that's our satellite, the moon, which was visited by the Apollo astronauts 50 years ago. If all goes well, will be visited again by the astronauts of the Artemis program within just the next couple of years. But now let's travel even farther out to cross that 250,000 miles between Earth and the moon. The Apollo astronauts took about 3 days to do that. However, we are going to start dealing with distances that are so great that we're going to have to use a different measuring stick. Astronomers usually like to use something based on the speed of light, which is the fastest known phenomenon in the universe. It travels 186,000 miles per second. If you could travel as fast as light, if you could travel 186,000 miles per second, you could travel around the Earth 7 times in 1 second. You could travel from Earth to the Moon in about 1.5 seconds, as opposed to the 3 days that it took the Apollo astronauts. But if you try to get to other planets in our solar system, it'll take you several hours in some cases, and we'll see some objects out there. As we travel farther away from our planet, let me put on the orbits of the other planets in our solar system, just so we have a better idea of where we are. So as we back away, we see the sun appearing at the bottom of our view, and the nearest planet to the sun is Mercury. Then comes the second planet, Venus. We on Earth are the third planet out, and then fourth is the red planet, Mars. Now, those are the inner planets of the solar system, what are called the terrestrial planets, or rocky planets. After that, after Mars, there is an area that's filled with lots of chunks of material, bits of rock and debris, known as the asteroid belt. And here in the asteroid belt, there are several 100,000 objects here. And in the entire solar system, there may be as many as 1 million asteroids. Not all the asteroids are limited to this area just beyond Mars. Some travel in closer to the sun than this region. Some travel a little bit farther out. So there are lots and lots of asteroids out there that we can see. And farther out, beyond the asteroids, there are what are called the Jovian planets. These are the really big planets of our solar system. There's Jupiter, and then Saturn, and then Uranus, and then the last planet, Neptune, out here. So those are the 8 planets of our solar system, which are now recognized by astronomers. A number of years ago, we used to recognize one other object as a planet, that being Pluto, whose orbit I've added just now. But Pluto has now been reclassified as a different kind of object. That happened back in 2006, and now it is recognized as a dwarf planet. And there are a few other objects in the solar system which are considered dwarf planets as well. But way out here, there is some other stuff, something like the asteroid belt, not planets, but there could be other dwarf planets in this area, asteroids and comet nuclei. This is an area that's filled with debris known as the Kuiper belt, also known as the zone of trans-Neptunian objects. This region here is filled with stuff, and it's a mess. I mean, you can see how much stuff there is out here. And this is one of the reasons Pluto is no longer considered a planet like Earth or Mars or Jupiter. One of the definitions of a planet that the International Astronomical Union decided upon in 2006 was that a planet had to use its gravity to clear its orbit of any other debris. And since Pluto is right here, smack in the middle of the Kuiper belt, clearly it has not used its gravity to clear the debris from that area. So it hasn't bullied the little guys out of its way. And that's why there's so much stuff out here. And that's why astronomers now have classified Pluto as a different kind of object, a dwarf planet. And as we travel even farther out, I'll add one more thing out here, which is, this is the paths of our most distant physical emissaries from Earth, the spacecraft that we have launched since about 1973 that have left the solar system. We'll zoom back in just a little bit here. The one going off by itself is Pioneer 10, which was launched in 1973. And then going off in the other direction is Pioneer 11, Voyager 1, and Voyager 2, and also New Horizons, which is the spacecraft that recently passed by Pluto and gave us a really good look at that object. But these are our most distant ambassadors from Earth. And they still have not traveled anywhere near any other stars. It's going to take them tens or hundreds of thousands of years to do that. In fact, the most distant of these spacecraft, Voyager 1, has not even traveled as far as light can travel in one day. So they're still pretty close to home as far as we can measure in terms of the rest of the universe. So now let's travel into interstellar space. This is the space between the stars, where we are now measuring distances in terms of light years, the length of time it takes light to travel between the stars. A light year, you may have heard that term before, is about 6 trillion miles. So it takes light 1 year to cross that distance, 6 trillion miles. And so as we approach other stars, we'll see distances that are several tens or even hundreds of light years. And as we travel farther and farther away from the sun, soon we're going to come to one other landmark, if you want to call it that. It is the distance that our most distant evidence of humanity has traveled. This is the farthest that any sign of the human race has traveled away from Earth. This is how far our radio signals have traveled in the past 90 years or so. Radio signals travel at the speed of light, 186,000 miles per second. And in the past 90 years, they've gotten this far out into space. And this is a distance where they have passed some stars, but not very many, and there's a long way to go. But these are early radio signals. Some of it was accidental radio noise given off by nuclear weapons tests, and later on from AM radio broadcasts, and they've gone out 90 light years into space. And an interesting thought here is that since it takes light and radio waves time to cross these distances, if there are any civilizations living on planets orbiting some of the stars inside this radiosphere, then they might have picked up our radio signals. So these stars here might know about us if they have life that has the technology to pick up our signals. But if there is any life on planets orbiting stars outside the radiosphere, they don't know about us yet. Our radio signals haven't gotten there. So we're going to find out that the universe is even bigger than this. This is nothing compared to the size of the entire universe. So let's continue traveling farther out. I'm going to leave the radiosphere on just so we can see our location in the Milky Way galaxy, which is now coming into view. And about 100 years ago, astronomers thought there was only one galaxy in the entire universe. They thought the Milky Way was alone. And then Edwin Hubble showed that there are other galaxies far outside our own. And not only that those galaxies are moving farther away. The universe is getting bigger because the galaxies are moving farther and farther apart. We, on the Earth orbiting the sun, are way out here, not at the center of the Milky Way galaxy, but about 2/3 of the way out from the center, on the edge of one of the spiral arms. You can see that our galaxy is a large flat disk of what astronomers estimate is several hundred billion stars. And it's so big that it would take a beam of light 100,000 years to cross the diameter of the galaxy, to get from one edge all the way across to the other. So our island universe of stars it's pretty big, but it is only one member of a cluster of galaxies that surrounds us. If we travel even farther out into space, we'll see some of the other members of this cluster of galaxies, which is known as the local group right here. The local group consists of, according to some estimates, as many as 80 small galaxies. There are 3 large members of the local group: our own Milky Way, the Andromeda Galaxy, and another galaxy called Triangulum. But every other galaxy in the local group seems to be a small galaxy, a dwarf galaxy. And this is a small cluster of galaxies. There are many others that are even bigger than this. In fact, now that we've left the galaxy, every spot of light you see on the dome overhead is not a star, but rather an entire galaxy containing several hundred billion stars, if not several trillion stars. As we travel even farther out now, we'll start to get some idea of the distribution of galaxies in the universe. There are lots and lots of galaxies. One very rough estimate that astronomers like to use is that there may be as many galaxies in the universe as there are stars in one galaxy. So on the order of several hundred thousand, or several hundred billion rather, but who knows how many there really are. As we travel even farther out, we begin to get an idea here of the structure, or rather the shape of our model of the universe. And I say it's the shape of our model because this is all based on our own observations from Earth of the universe around us. Where the galaxies are, how many there are, this is based on actual surveys. So this is all real data that we're looking at. Now, something might occur to you that might give rise to an interesting question. Does our universe really look like a big butterfly? Or maybe in some interpretations, a big hourglass. It has two big fans stretching off in either direction from one side to the other, and a rather empty space between them. Is that really the shape of the universe? Well, it's the shape of our model, because that empty space is not empty space. It's just parts of the universe that we haven't had a good look at yet, because something is blocking our view in that direction. And what's blocking our view is the disk of our own Milky Way galaxy. This is lined up precisely with the plane of our flat galaxy. So the dust and gas along the plane of the galaxy is preventing us from seeing a lot of the galaxies that are out here. Eventually, as our technology and techniques get better, we expect to see more farther in that direction, and our distribution of galaxies in the universe will even out. It'll be more uniform in all directions. But right now, this is the shape of our current model of the universe. And as we travel even farther and farther out, you can see that the texture of the universe is, might describe it as foamy. It looks kind of sudsy with the filaments of galaxies separated by large empty spaces or voids. And farther out, we encounter some of the most energetic things ever observed in the universe. We observe strange things called quasi-stellar radio sources, or quasars for short. These are objects that were discovered in the 1960s and which were found to be very, very bright. And considering how far away they are, they must be tremendously energetic. They're represented by the orange spots at the ends of the fans that you see here. These are on the order of about 10 billion light years away, near the edge of the farthest we can see into space. Now, astronomers think, or one of the current theories, is that quasars are the cores of young newborn galaxies powered by supermassive black holes. And they think that almost every galaxy has a supermassive black hole at its center. Even farther out than that, the farthest we can see in the universe at all is where we find a faint radiation called the cosmic microwave background. This is a faint radiation coming from all directions. It permeates the entire universe and is as far as we can see into the cosmos. This faint radiation is said to be the leftover radiation, an echo of the Big Bang, the moment in time when the galaxies began to expand away from each other. And many astronomers say this is the best evidence they have for that phenomenon, that point in time. But this isn't really a visual map of the distant universe. This is more of a heat map. It shows the distribution of areas which are a little bit warmer than other areas. And this shows astronomers the beginning of the differentiation of matter in the cosmos and how stars and galaxies began to form. The universe was not totally uniform at the very beginning. There was this mottled effect where some areas are warmer or cooler than others. And this is as far as our astronomers can see. Way out here, about almost 13.8 billion light years away. And since this is the edge of the visible universe, there's only one place we can go, that's back in toward where we came from. And so as we do that, we're heading back in toward what looks like the center of our model. And it might make you wonder whether or not we really are at the center of the entire universe. But again, remember, this is just a model based on our perception. It looks like this because we're the ones who made the map. We made this model, and it's based on our looking around us in all directions. If somebody else were in some other part of the universe making their own model of the universe, it would look similar, only they would be at the center of their model. So the universe is a huge, huge place, and it is just one mind-boggling thing after another. As we pass all these distant galaxies filled with hundreds of billions of stars, you might wonder whether or not there are other planets orbiting these distant stars. And in fact, it turns out that there are. As we approach our radiosphere, we'll start to see a map of what are called the extrasolar planets, or exoplanets. These have been discovered since about 1994 and are stars that have been found to be orbited by at least one planet. So there's our radiosphere, and fanning out from it, as you can see, those light blue markers are the locations of stars that are orbited by planets. Since 1994, more than 5,000 other planets have been found orbiting distant stars. So with so many planets now being discovered, and those are just the nearest ones to us, the easiest ones for us to see. And with so many planets out there that are confirmed, are any of them like our own world? Are any of these other planets like Earth itself? Well, we don't know for sure, because it takes a certain set of circumstances that need to be fulfilled in order for a planet to be considered Earth-like and able to support life, if you want to use that definition of the term Earth-like. There are many rocky planets, but a lot of others are very gaseous. Some are very close to their stars. Others are very far away, so they're either too hot or too cold. A planet has to orbit the right kind of star that doesn't give off dangerous levels of radiation, and it has to be just the right distance from its star so that liquid water can exist. It exists in a temperature range that allows liquid water to survive. So those are just a few of the conditions that are required in order for a planet to be habitable in some way. And so far, in our travels through the cosmos, away from the Milky Way, through the other clusters of galaxies that we can see in space, we find that our own planet, Earth, is the only one that we are aware of so far that fulfills all those conditions and allows life to exist. So as we approach our own home planet, we come to a sobering realization that there is no place like home. And with that, let's take good care of our planet so that it can continue to take good care of us. With that, welcome back home to planet Earth, and we hope you have enjoyed our tour of the universe. Thank you very much.